All right, welcome back. We're going to be talking about some properties of integrals, and then we're going to roll that into something called an antiderivative. We'll talk about what that is when we get there. But let's start by just thinking about integrals. So we've got an integral from a to b of some function f of x with respect to x. And we know that this is defined as the area under the curve in the interval AB. So if I think of this on a graph, I've got some interval going from A to B. Here's the x-axis, and I can say that that integral is equal to that. Well, let's define a new integral, and I'm going to call this one the integral from B to C of the same function with respect to x. And I know that this is the area ... under the curve, but it is from B to C. So I'm going to add a C, and we know that this new integral is this area. So it follows, therefore, that the integral from A to C of this function is quite clearly just the sum of the integral from A to B plus the integral from B to C. So a lot of our properties are going to just come out of a basic observation of, oh, look, if I take this and I take that, and I can do this to it. So let's look at another one. Let's look at the integral from, change colors again, the integral from a to b of f of x dx plus the integral from b to a of f of x dx. Well, according to our previous rule, this should just be the integral from a to a of f of x dx. And that must equal 0 because I have an interval width of 0. So taking that one a little bit farther, now we know that these two add up to 0. If I subtract this right-hand one from both sides, what I get is that the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. So what we've just discovered is that if we go in the opposite direction, we're taking the exact same area, but it's a negative if we're moving to the left versus a positive if we're moving to the right. All right, so there are two things that we now know. Number one, that is a property of integrals. Number two, this is a property of integrals. Let's look at a couple more. So how about a constant multiplier, constant multiple? Wow, my pen just went crazy there, but there it is. The integral from a to b of k f of x dx. Well, let's just very quickly think about this function. Here's some function. And here's the integral from a to b. Well, if I double the function, we'll call this f of x, every rectangle gets twice as tall, which means that the area gets twice as big. Now, applying this to any constant, we could just take the constant out and say, well, no, let's just find the integral from a to b of f of x dx, and then multiply it by whatever our constant is. So there's number 3. Let's see, what else have we got? Sum and difference. We're going to call this number 4 right off the bat. Sum and difference. The integral from a to b of the sum or difference of a function. Well, you think about stacking two functions on top of each other. The area is just going to be the one plus the other, or minus the other, depending on which direction we're going. So we know that this equals the integral from a to b of the first function with respect to x plus or minus the integral from a to b of the second function with respect to x. Here's a fun one, the Max Min Inequality Property. So let's look at a quick graph. I've got some graph, here it is. So let's think about what the minimum area under this curve is. Here's A, here's B. If the function were to never go above that height, then the area would have to be that, which means that the actual function has to be greater than that. So this is our minimum area, which is the minimum value of f times the width. It's a rectangle. Okay, so let's look at another rectangle. What if I were to make a rectangle that was the highest that this would ever go? This is my maximum value of f. Well, clearly the area of this rectangle is the maximum value of f times b minus a. And here we go, just as clearly, the actual value can't be less than that red rectangle. It can't be greater than that green rectangle, which means that the actual value of the integral from a to b of f of x dx must be somewhere in between these two values. And this can be useful because let's say you don't really have the tools to prove the actual value of the integral, but you can say, well, we know it has to be bigger than this, and we know it has to be less than that. So boom, there it is. We know it's in here somewhere. That could be a useful thing to know. Let's see, the last one, and then I will stop this video, is called Domination. And basically what Domination says is that if f of x is greater than or equal to g of x on the interval, then the area under f of x has to be greater than or equal to the area under g of x. And I'm not gonna prove that one. I'll just let you accept that one as a, hey, look, there it is. And I think it seems pretty obvious. F is higher than g, well then this area must be bigger than that area. So, and there's a one that goes along with this, says, well, what if g of x is equal to 0? So then you can also conclude that if f of x is positive on the interval, then the integral of f of x, the area under that curve, must also be positive. We decided to go with positive, not not or equal to. So anyway, I guess we could, let's stick an equal to in there. There we go. There's a few properties of definite integrals. If you are in my class, you can turn to page 293 in your textbook, and you'll see a table listing all these properties. And we'll be back with some examples of how we use them. Thanks for watching.